So let me start today's class. It's again on approximation theory, and most of the results I'm going to speak about are in a couple of papers with co-workers. The main one being Hrusikesh Maskar, who is an approximation theory expert. You will have on the web later today also a link to slides and to a video of a talk I gave in Stanford a month ago. And a third of the slides and the video cover approximation theory. The rest is about the next two classes. The next one on Wednesday will be more ongoing work about optimization for deep networks. And the one a week from now will be on generalization and the puzzle of no overfitting by deep networks. And the last one will be about some speculation on new architectures for learning, different from deep learning, that are suggested by neuroscience. So let me start today with a brief summary of what we proved last time, so in the first class. So there were basically two main results, but I list here four just for completeness. One is the observation that both shallow networks, one layer, like reproducing kernel machines, or similar, classifier just one set of weights, one set of nonlinear units. Those, as well as network that I will call, and I will explain later why, I'll call hierarchically local deep nets. So convolutional networks are a special case of those. Okay, both these shallow and deep nets are dense in a compact domain on continuous function supported on a compact domain, on the real numbers, right? For instance, 0, 1, or whatever you want. That means that they can approximate within epsilon in the sup norm any continuous function. And we mentioned that this was one reason why when this result came out in the 80s or so, people kind of focused on one-layer networks because shallow networks are enough for doing this approximation. However, we saw that if you look at shallow networks and you now look, okay, they are dense, but how many units and parameters do I need to approximate a function? Then it turns out that they are under the curse of dimensionality. In other words, if I have a function that is in the Sobolev space dm, this means function with d variables, the inputs, and smoothness m, derivative up to degree n, then, and G is a shallow net, then in order to have an approximation within epsilon, I need to say that I need n, capital N units in the order of is 1 over epsilon to d over m. And take m just one, so only one derivative, for instance, then epsilon say is 1/10, so this becomes 10 to the d, and for d large, this is very, very large. So that's the curse of dimensionality. And I'll say later, this is an upper bound. So if I have that, I guarantee this epsilon approximation. Okay. However, we can prove that for certain functions that are in what I'll call, for simplicity now, D2M. So these are functions that have D inputs, as many as I want, but they're made up of functions, constituent functions, that have two inputs, two variables. Okay? Instead of two, I can use something else, but let me take two for simplicity. And so in this case, if G is one of these deep nets, then F minus G less than epsilon, this is what I want, a good approximation. I can guarantee that with a number of units which is in the order of D minus 1, and then I have 1 over epsilon 2 over m. So D can be very large as I want. The larger D, of course, the more layers. And the number of units increase linearly with D instead of exponentially. So this means that for certain classes of functions, deep networks, I can have this guarantee that deep networks will approximate those arbitrarily within epsilon with this number of units. And I cannot guarantee this for shallow network when approximating these compositional functions. Okay? The fourth is just a corollary in a sense. If you want to think about polynomials, then instead of this function, that the same thing, the same two results hold for polynomials. So suppose the function I want to approximate is a polynomial of with d variables and degree k, then if I have a shallow network, so G shallow, if I want to have F is a polynomial, G shallow, if I want to have F minus G less than epsilon, I'll have to say that I need N, a network G shallow with a number of units in the order of K to the D. These are, by the way, the order of the number of monomials in a polynomial, generic polynomials with this D variables and the. But if I have F that is a polynomial that is made up of quadratic polynomials, each one in two variables. Then I can guarantee epsilon approximation with a number of units which is in the order of d minus 1, and then will be k square, because that's the number, the terms that I need to approximate a quadratic polynomial, a polynomial of degree k in two variables. Okay, so that's essentially a summary of what we did last time. And let me show you a couple of experiments. Numerical experiments with networks, just. Thank you. So forget this for a moment. Up there, you have graphs of function. This is a generic function of 8 variables up there. And here you have a shallow network in 8 variables. So this is this will be the curse of dimensionality. If you want to approximate a generic function, you don't have any specific information about its structure. But if you know that the function is hierarchically compositional, so the structure of the function is this binary tree up there, where each red node is a function of 2 variables, then if I try to approximate it with a shallow network, I still have the same problem with the curse of dimensionality, because this network does not know about that structure, cannot exploit it. But a network that essentially has a similar structure to the function graph, where each node is a set of units, this network will be able to escape the curse of dimensionality. And the next slide, let me go to, shows, for instance, trying to learn a function that corresponds to a compositional function using a shallow networks, and this is for different number of parameters of the network, 9,000. And approximating the same function with the deep networks works much better. So, and you can do this also on more real data sets, like I think I did show this slide at the beginning of the course, but on the left you have training error. And here you have, it's just iteration of gradient descent. We'll speak about gradient descent, actually stochastic gradient descent, next Wednesday. And you have the error, the training error you can have with a shallow network, 2 layers, a deep one, so the deep, let me take, consider just the blue, and this one will be a network like the ones I called hierarchically local network. And the bottom one is a hierarchically local network in which the local function at each layer are the same. This is weight sharing. Okay? So if you have a function that is, in addition to be hierarchically compositional, is also as this translation invariant structure, if you think about images, then not only these local functions, the constituent functions are local, but they're also the same at each layer. And this reduces the number of parameters, it reduces the complexity of the networks, and so that's the best situation. But as I said in the proof of the results, weight sharing is not the key part for avoiding the curse of dimensionality. The key one is the locality of the functions. Okay. This is recent work, so there is quite a bit more empirical work and theoretical work that could be done. You have not done enough of these experiments. There are certainly more to do. And several of the things I'll speak about next are really, all of them are probably, projects one could do, research projects. Can I have the whiteboard again? Thank you. So, let me go through a number of other remarks, consequences, open problems here. One of them has to do with the following fact. I don't know if you noticed, but the networks I've been speaking about have several units here and one output. Okay, so in one. Okay, now most of the actual networks that people use have the same situation. For instance, in the networks used for cipher, instead of 2 inputs, you have typically a kernel which is 3 by 3, so essentially 10 inputs. So you have 10 instead of 2, but everything is the same. But the output of each node, here you have different units corresponding to different channels, is not just one output. You have, from this node, you have inputs going everywhere within, again, a channel. So you have, instead of having one, a function that is taking values on the reals, you have a function that has a vector output. And so one question is, do our results apply in this case? And the answer is yes, and it's somewhat not intuitive. The fact that if I consider a function that is going from, say, d variables to q variables. So until now, our q is 1 for each node. Then, if I want to guarantee a network approximating this function, let's call the network, let's say, call it S. So let's say this function, I consider the components of I, the output is Q, so there will be Q components, Q functions, and I consider each one of them, and I want to approximate each one of them with the output of the network, and I want the approximation to be less than epsilon. And it turns out the number of units that I need in the network that does that for all I is no larger in the case I have Q equal 1. So it's still the order of epsilon to so having an approximation of a multi-valued function or having an approximation of a uni-valued function requires the same number of hidden units. Okay? And the intuition here is that when I have units, so I have 2 inputs or 10 inputs and have a set of units, and now I have from this a lot of outputs, each one with his particular weight. Think of this set of units as corresponding to monomials in a polynomial that is approximating a function, okay? And now I can, through the coefficients here, linear combination of them, I can combine them in different way to approximate any appropriate function I want. So I essentially reuse those hidden units for the different components of the function. Okay. Somebody? Okay. There are some interesting implications that I don't have the time to go over and that I did not explore, but maybe interesting for future work because if you are interested in compressing a network, so reducing the number of units and parameters, and people are starting to be interested in this for hardware implementations, for instance. Then considerations along these lines tell you something about how many parameters you really need from one layer to the next, and how you could compress them by doing something similar to PCA. I don't think that's important for performance. It's only important if you want to compress the architecture of a network. Okay, so so again, a summary of the result and the main result and a generalization of it is that if you have a graph, if you have a function, let's go back to one output, so it's from RD to R, and the function can be, as a structure, is compositional, but it's not a binary tree. is a general acyclic graph, a directed acyclic graph. So G is a DAG. It has D sources. These are the inputs. And suppose that each vertex in the graph has dv, so this is one node in the graph. It has dv inputs, the subscript v inputs. Then a network with a similar architecture, where each node is a set of units, will need a total number of units that is in the order of n will be the sum over all the nodes in the graph. And then I have the usual term here, dv over mv, where dv is the dimensionality of node v, and m is the smoothness of that function there. And I could even define this as the effective dimensionality of the function at v. So again, this is mainly to say that the results that I showed for binary trees can be easily extended to more general compositional structures. Okay. So any question? One lesson from this is that your prior knowledge about the problem you have to solve could be related to the nature of the functions that you are trying to learn. For instance, if you have some reason to think that the function can be decomposed or represented in terms of component functions, give you some very useful hints about the architecture of the network. So at this point, your prior information is not in the learning algorithm or how you run the machinery. You can just use whatever software you have. Your prior information is really in the architecture of the network. How many layers, how local the kernels are. It is convolutional in the sense, its locality is important. Do you have some guess about how local the layers you have or you should have? And do you have some invariance properties for having weight sharing at one layer or across layers? And again, this prior information does not need to be used in an exact way. That's one of the great things. You could have, suppose you know its locality, but if the real function has, say, 6 inputs for each constituents function, and you have that instead have 12, you're fine. It's you're maybe not as optimal as you could be, but okay. So let me say a few more words about the word compositionality, because this can be a bit confusing, especially if you look at literature. There are two meanings in which I have used this. Originally, the reason for using the term compositionality was in the same spirit as it is used in especially language and text, and to some extent in vision, where you have the idea that high-level concepts are composed of a small number of lower-level ones, like an object is composed of parts, a sentence is composed of words, a word is composed of syllables, syllables are composed of letters, and so on. So that's one meaning of it. And this really corresponds also to this structure, for instance, of a binary tree graph, where you have variables that come together in a node, and nodes come together in higher level nodes. But then there is the other use of compositional functions that is just a function of a function. Right? And so that's why I've been using the term hierarchically local compositional functions to denote functions that have this particular compositional structure. The term's compositionality for a function does not really mean they should be local and compositional in this way. Okay. Another point again, that's relevant for understanding some of the literature is the difference between upper bounds and lower bounds. It's a very technical thing, but just to put this clearly, these are upper bounds in the sense that if I have functions like this, then I give you some minimum number of units for which I can guarantee this approximation for any function. But it could be that I have a particular function f, just a very specific one, for which I could find a shallow approximation with fewer units. This would be this possible. So a lower bound would be exhibiting a function for which this is not possible. Okay, for instance, functions that cannot be approximated by shallow units with fewer than an exponential number of units. And several of these lower bounds were known. Chewy and Mascaret found papers on them like in 95 or so. More recently, there's been an interest again, especially from people from computer science theory. And one interesting example comes from the work of Tegalski, who essentially he finds that functions that are produced, certain functions, specific functions, that have a very large number of oscillations relative to the dimensionality, can be produced by a deep network, but cannot be approximated by a shallow network with less than exponential number of units. Okay, this is really, as I said, more of a technical results because a shallow network cannot really exploit, does not know about the compositional structure. So it's to be expected. An interesting connection here, and the reason, for instance, for this result is because of similar results in the 80s about Boolean functions. Okay, so how many of you are from computer science? Okay, not too many, but in computer science, Boolean functions have an important role. Of course, computers are running on them. So Boolean functions are functions of Boolean variables, false or true. So they are functions that map -1 plus 1 to the d into, now, the function itself usually can take also a binary value. So -1, 1. But it could be also a real value. Does not really matter. They're still called the Boolean functions. Okay. Now, in the 80s and 90s, there was quite a bit of interest in results that tell you how complex a circuit has to be in order to implement a Boolean function, or also results about learning Boolean functions from examples. And it's interesting still today because it's, you can learn rules this way and a lot of other things. So let me tell you a little bit about Boolean functions. This is something that I didn't know and I learned in this work about approximation. Because there is a close connection with this kind of curse of dimensionality results. So the first thing is to introduce what computer scientists called a Fourier representation of a Boolean function, which is really a misnomer because a Fourier representation of a Boolean function is really a polynomial representation of a Boolean function. To some extent, it's kind of misleading to use the term Fourier, but so for instance, suppose I want to represent, this is really exact, it's not approximation, it's exact representation. Suppose I want to represent the Boolean function max2. So this is the max over 2 Boolean variables, x1 and x2. So, I can list the table of this function. So if x1 is +1 and x2 is 1, the maximum is, of course, +1. If x1 is +1, and let me follow these notes. -1 + 1 is still +1. If it's +1, 1, it's +1. And if it's -1, -1, it's -1. Okay? That's the truth table of the max function. Now, it turns out that I can represent this as the following polynomial is 1 plus x1 plus x2 minus x1 times x2. This is polynomial in the variable. By the way, people sometimes use for the Boolean variables 0 and 1 instead of -1 and 1. But for this kind of things that I'm going to do, the -1 plus 1 is nicer because, right, you can do it 0 and 1 becomes more complicated. Okay, the way you can do this for any Boolean function to represent it as a polynomial in the variable is to use a classical way to represent a polynomial that comes from the fundamental theorem of algebra, which is really represented with their roots. So in the case of a polynomial, suppose that I have a polynomial that takes values over the 2 over d values of its inputs. So you have Boolean variables. So you have 2 to the d values on the Boolean cube with d dimensions. And this function assigns -1 or +1 to these vertices of the cube. And so for each one of these points, if I say the coordinates of one of these 2D points are A1 to AD, and this is in -1, 1 to the D, then the indicator function of this function is, let me denote it as 1 A of x. This would be 1 plus A1 x1 over 2, 1 plus A2 x2. These are so these are 1 plus AD xd 2. And so what happens is that when x is equal A1, then this is 1 and everything else is 0. Okay? Okay, so then the function itself will be represented as the sum over all the vertices of the cube. So this would be -1, 1 d, the value at each one, and this is this indicator function. So that's one way to represent a function. You can do this exercise for the max2 function. You will see that I have the value of the function for the first A. This is a +1 + 1. So I said it was +1. And then I have the indicator function 1 x1, 2, 1 plus x2, 2. So that's the first. Then I will have +1, I have 1 minus x1, 1 plus x2, 2, and so on. So this polynomial, by the way, are also called multilinear because they are linear in each of the variables. There is no x1 or x2 or whatever. They never appear as squares or cube. Squares, of course, would be 1 anyway. So, and furthermore, this is a representation that is so these terms here are so-called parity functions. So functions, for instance, of two variables taking the value corresponding to how many of the variables are even or odd. Now, why I say this is because a result that is actually was proven by a student at MIT in the 80s, Hastad, which actually generalized slightly some previous results by Sipzer, who is now our Dean of Science. He proved that there are certain functions, Boolean functions, that are exactly the parity function. So for instance, if you have d variables, it would be like the products of all the d variables that can not be represented efficiently by a shallow circuit, but can be represented efficiently by deep circuits. And this is exactly the Boolean correspondent of our results. So in a certain sense, you could say that this kind of results that we have are an extension to general functions of this, all the results for Boolean functions. Okay. Now, these connections, as I mentioned, there is certainly more work to be done. There is a conjecture, for instance, that multiplication of real variables, which would correspond to the parity function of Boolean variables, cannot be approximated by a shallow network with less than exponential units. But there is a proof in a paper by Max Tegmark, but I don't think that's correct. So that does not mean that the statement is. Again, that's a project for future work. Another interesting connection of this kind of result is with vector quantization. So vector quantization is essentially similar to clustering, and it's used in a number of compression schemes. For instance, JPEG or MPEG. You can think of them as saying, okay, instead of representing 8 by 8 pixels in the image with 16 bits numbers or whatever, I have a short dictionary of basic configurations that I can have. And when I get a new image, I look at this block 8 by 8, and I look at what is the most similar one in my short dictionary, and I'll send that. And that is, of course, I don't need to send the actual 64 values. I send just an index, a number saying which block I want to reproduce. So that's quantization. And you can think, in a sense, that radial basis functions, or in a sense, reproducing kernel Hilbert space machines are doing something like this, because you can imagine inputs X here. Here is a set of examples, and the output is the sum of Ci of G X Xi. This usually measure the similarity with the dot product or the distance. So for instance, if this is Gaussian, this would be e to x minus xi square. So this will be 1 if x is exactly the same as xi. And this would be exact pattern matching. But if it's similar, depending on the sigma, I can send the value I want corresponding to it. This is a form of soft vector quantization. Okay, so suppose now that I think, how could I generalize vector quantization to hierarchies? And there is, in fact, a small field, I found only 3 or 4 papers, called hierarchical vector quantization. And the idea is essentially that instead of having a dictionary for my 8 by 8 blocks, what about if I could identify a basic number of blocks, and then I could reuse them in various configurations? So imagine that, some of these blocks, again, thinking about images, could be, this is correspond to an oblique line, an edge. And this may correspond to another one. And with vector quantization, that's it, what I do. But suppose now that I want to compress even more. And so now I can say, if this is present and this is present, then this is this pattern. So I don't need to send this and this. I can just send my index for this one, for this corner. But then I can do it also for this one, if I put this together in a different way. So in other words, if I have a structure that is hierarchical, where I have parts, objects, and collections of objects, then I can compress even further if the basic parts are used in different ways. And that's, again, very similar to what we have discussed in terms of hierarchical compositional functions. So there is a field here. I don't know whether people have used deep networks for compression, but could be used in this way. Now, there is also another point of view that I find interesting. Here, we have addressed the approximation question is by following a route that standard approximation theory, which is a field which is older than computer science, followed, which is polynomials. It's really Weierstrass theorem. Using polynomials, you can approximate anything, and there are more technical results by people like Devore and others. I mention name in case you find papers about that say that what polynomial can do in terms of approximation is, in some technical sense, the best. So you cannot hope to find better techniques. But from the point of view of what neural networks are really doing, do we believe that they do combination of units to approximate polynomials? Probably not, right? So is there another way to look at it? So having this idea of functions, compositional functions, but thinking how I could combine rectified linear units to approximate this function. And so let's consider how I could use RL units to approximate a function of two variables. If I can do this, then everything else follows from this hierarchical and compositional structure. Here, what we did was to say, because if I have a nonlinearity, which is not a polynomial, then I can approximate by combining linearly units any univariate polynomial. And by combining univariate polynomials, I can approximate any multivariate polynomials, and then any multivariate polynomials can approximate Sobolev function. This was the sequence of arguments. But if we say, okay, let's forget about polynomials. I'll assume that my function is just Lipschitz. So Lipschitz function means it is a function such that the norms of fx1 minus fx2 is less than some constant called the Lipschitz constant. So basically is a limit to how much the function can change, and differentiable functions are Lipschitz, and piecewise linear functions are Lipschitz, and so on. Okay, so that's what I assume for the function. Now, if I assume this, then if I have a bounded interval in a variable x, say from 0 and 1, I can, if I know the Lipschitz constant of L, I can decide how many elements in a partition of this I need in order to approximate the function with piecewise pieces on this partition, so that the error is less than epsilon. I can make this partition dense depending on the Lipschitz constant of H, okay? And depending how much error I want, how big epsilon is. Okay, so I have a partition of X. I can do that for each one of the two variables. And now I have to represent the value of the function on a partition on the cube, on the square. So what I can do is I can I have to find out when in a network Suppose I have an input, I have x. I have to find out where x is. How can I do that? By combining 4 RLUs, I can get a good approximation to the indicator function. Okay, so suppose I have only the x partition, then I want to know x get into the network, and I want to say if x is between x between 0 and 0.2, the value of this one variate function should be, for instance, f of x equal a, okay? So I need here a nonlinearity that is 0 unless x is between 0 and 0.2. If this happens, then it's 1, and then the coefficient here would be give me the value of the function. And if I have enough units, I can do this for the different partitions. I can represent the function in terms of this constant spline, piecewise constant spline. The problem is, how do I do this in 2 dimensions? Now I have to say not only x1 has to be between 0 and 0.2, but x2 has to be between 0.4 and 0.5. It's an AND. How do I do the equivalent of an AND or a multiplication with RLUs? Here I made this indicator function by combining an RLU like this with, let's see, linearly with another one which is like this, and then another one that will approximate. Sorry?
How would you get this step?
Well, you don't get exactly the step. You get, so this construction works if within epsilon, and I'm assuming that we are, that's why it's a computer science point of view, it will not work in classical analysis, but it works if I assume I have discrete numbers, right, effectively. Yeah, that's the basic trick here. Yeah, good point. And but produce an AND or a multiplication. It turns out that I think free, let's see, I can synthesize this function x, y. These are not Boolean variables, are real variables by x plus y half plus the absolute value of this. It's kind of interesting. It's not completely obvious. Because if, let's see, if suppose x is less than y, then that remains, and this will now be negative, and so the absolute value will change it, and so I'll have minus y plus x, and I'll have x, and so that's x is the minimum of the two, and so things will work. Okay, so that's interesting that I can do minimum with linear combination, and here I need the absolute value, but if I have the RLU and I add another RLU with a minus sign, I get the absolute value. Sorry?
I think you need the minus. It's X plus 1 over 2 minus absolute.
Yeah. Oh, the minus, yes. I think you're right. Let me see. Thank you. Yeah. So basically, I can have an indicator function that for this partition on the square, and then another indicator function for this one, and then I can get with the coefficient the value, I assign the value that I want. So I can build a network that will get as input x and y, and will approximate a two-dimensional function in terms of piecewise constant values. And the indicator function for the two variables is built through this. Right? Okay, so the interesting point here is that if you compute how many units do I need to do this, you can do that, but the number of units you come up with is in the same order as the case of the polynomials. No different. So you have the same kind of results with curse of dimensionality or winning against the curse of dimensionality. And the reason is simply that you have terms like k to the d, where k here is the degree and there is the number of partitions. You know, if I have k partition in one variable, when I have d variables, I now have k to the d partitions. And the number of units I need for each partition is then proportional to that. You know? Now, apart from checking that, you know, these results do not depend on using polynomials, they're kind of more general. This also is potentially a more intuitive way to describe how neural network may approximate a function. So it's kind of, you know, piecewise constant approximation in that sense. And one important notice is that here, in telling you how to build this, I started saying we can decide what our partition is, how many elements, and assuming they are this equidistant, depending on the Lipschitz constant. But you could assume that if I have a greedy approximation, I could optimize the spacing and maybe the number of partitions, so to minimize how many elements I need. And this is what is called, in, again, approximation theory is called free nodes splines. So splines technically are piecewise polynomials. So for instance, in one variable, a typical spline will have some nodes, and I interpolate a function. This is, for instance, linear spline. So this is standard splines, and instead of the linear terms, I could have constants, which is the example I was describing, or I could have cubic, pieces of cubic polynomials, and that's the one that was used. It was, by the way, was developed by Schoenberg in the 40s in order to compute numerically acceleration and speed for rockets that were tested in New Mexico or something from observation of the trajectory. He needed to have an approximation that he could take derivatives of. So this is the standard splines. But the free node splines, the one which, depending on the function I have and measuring the error, I could change the position of the nodes. And that's in a sense, what networks are doing, because they're effectively, the partition is not set, the weights can be changed at all layers in a greedy way, and of course, there are very few theoretical results on free nodes splines. So that's not surprising. There are few results on neural networks as well. Okay, let me see. Just to finish in time, let me discuss this more philosophical question of why compositional functions. So what I've been telling you is the better way to formulate this is a conjecture about why neural networks, one reason why neural networks are working so well compared with shallow networks. So that's a conjecture in a sense that rests upon the assumption that the functions are involved that you are trying to learn when you're learning, say, classification on ImageNet are functions that are compositional. A better way to describe what I told you is to explain why neural networks do not seem to have this curse of dimensionality, which you would expect from basic considerations of approximation theory. But if you stick to what I said, conjecture that they work well, and so it inescapable the conclusion that these various things we are very interested in, like classification of images or classification of text, all the applications where convolutional networks have been successful. If they are compositional, this tells you why deep networks work in those tasks and shallow networks don't do as well. And by the way, that's for convolutional networks. Dense networks in this theory don't have, they should not work very well, okay? Okay, so why compositional functions should be so important here? Now, it seems intuitive that in the universe of all possible functions, variables, it seems intuitive that somebody could prove that the hierarchically local compositional functions have measure 0. There are many more that are not. This seems my intuition. I don't know if it's true, but it's reasonable to assume that. If we assume that, then why it seems that many interesting problems are compositional if this interpretation is correct. And Max Tegmark, a colleague of mine in the physics department, has this conjecture that this is because of physics. So he's trying to explain especially why images or classifying images should be compositional. And the argument is, as you can see from the graph like this is kind of saying that pixels that are far apart don't interact very strongly. They interact up here, but not at the low level. And the argument is that this is because physics is local. And so the universe is based on interactions, say, various physical forces, electromagnetic and gravity that are basically local, and creates clusters of matter, starting with from galaxies down on. It's like saying that's why there are objects and parts and big objects and smaller objects and so on. I'm not sure I find that very convincing. Another, but it is Mach's thesis. The TP thesis, my thesis, is that is because of our brain. Suppose that evolution wires up our cortex, and we know that's true, actually, for cortex and especially visual cortex, with local connectivity. We know that in visual cortex, there are neurons in the retina that really look at only a few pixels, each one of them. And there are neurons later on that look at a small number of neurons and so on, really with a structure that is very similar to this, where these are pixel or photoreceptors in space. So why does evolution do that? Well, maybe it's simply because it's much easier to for the genes to encode information about local connectivity than long-range connectivity. It's easy, or very difficult to build precise long-range wires just based on genetic information. But it's easier to encode local connectivity rules. Okay, but if it's so, then for instance, our visual cortex would be wired up to be a deep network. And then a deep network can deal well with compositional functions. And so these are the problems we can solve. That's the problems we're interested in. So that's the other argument. There is a third one, which is kind of a summary of both, which is more from the computational and computer science point of view. If you think about, and this is again essentially a project, it would be nice somebody to do some work here, but you can think of something like this. So this symbol means that I have a function of inputs x, and there are other inputs that are parameters, that are, for instance, telling me how many outputs the function should be. Or, I can basically parameterize this in a very flexible way. And then I have a function, so this would be f2 of this. And again, this function will output some output and some parameters, and this will read it and do the same. So if I write it in this way, this is a Turing machine for unbounded n. I really can compose a set of operations on top of another, and depending on the output, do the rest. So, so the question is, we know that a Turing machine, so it's really a composition of functions, and there is this kind of axioms, or called the Church-Turing Thesis, that the functions that a Turing machine computes are all computable functions, or all computable functions can be computed by Turing machines. And furthermore, the functions are, every function that computed in this way can be built in a compositional way from elementary functions. For instance, you can build any function from multiplications and additions and a couple of other, or any small choices you have. So one could maybe almost say that hierarchically local compositional functions are effectively the computable functions when you look at functions of many variables. So a claim similar to basic theory of computer science of what it means to have computable function. When I mean effectively computable, means that how can I compute effectively a function that is exponential in the number of variables, right? It is computable in the strict sense, but it's effectively, it becomes impossible to compute when the variables are large. This is in a sense a repeating the other two point of views of Mach's thesis and TP thesis, because it basically says that the compositional functions are the only one you can deal with, and so are the only practical functions that for all practical purposes exist. Okay, so let me finish here, and as I said, next time we'll switch to why quantization is so easy for neural networks, for deep networks, despite being, in principle, NP complete and quite difficult.